Thank you very much. Now, I know you've all heard a lot about space, what I call real space exploration. So, what I'm going to do is bring you very literally back down to Earth to look at the hugely important role that space science can have on every single one of us. And I thought I'd start with this presentation with a time-lapse sequence of imagery recorded from the International Space Station, which I'm sure you know is orbiting at an altitude of about 400 kilometers above the Earth's surface. Now, this beautiful sequence of imagery is actually an extract from a friend of mine and a digital space artist, Sean Duran, who takes imagery from space science missions and generates artistic pieces from them. Now, other than being beautiful and a complete wonder to look at, these images really show and perfectly highlight the unique perspective that can be gained by stepping outside of Earth's atmosphere. Now, Earth observation from satellites enables us to observe all parts and extremes of the planet that we live on. And we're able to do that on repeat timescales from several days if you're in low Earth orbit through to continual observations if you're in geosynchronous orbit. And due to the stability and the way that we make these satellites, we can design these so they continually observe for years at a time. So this talk is really going to be focused on the importance of Earth observation in the fight for, and effectively, I think, an existential threat faced by humanity due to climate change, which is due to its very nature, impacts every part of the globe and every aspect of our day-to-day living. Now, I do class myself as a planetary scientist now, and you might recognize that Earth is a planet too, is one I'm very attached to. But I actually work as an Earth observation scientist at the Rutherford Appleton Laboratory, RAL Space. Now, this talk is going to be part motivational, it's part going to be demonstrating the importance of space and Earth observation, but it's actually a really great excuse to show an incredible range of footage shown, such as this, of Earth. So when we talk about global challenges, there are many different threats that face humanity. There are also many different ways to define and prioritize these challenges. One of the most easily digestible, if potentially not the most depressing, is produced by the World Economic Forum's assessment of the greatest present-day risks. Now, on the face of it, this document may look quite dry, but actually it's very insightful because the World Economic Risk Report is published every year and details the biggest risks on global pressures on the economic future of the world. Now, in this risk diagram, hang on, let me bring up my laser pointer. Each diamond refers to a different risk, where each color is defining a different sector, where green, as you see at the top, being the environmental risks. Now, I don't really expect you to be able to read and understand all of the links between these risk points. But what I do want you to take away is how complex and how highly interconnected they are. Now, this is an interesting figure because it was taken from the 2020 risk report, which was published in January 15th of last year, a month before the global pandemic hit. And you will notice in the top left-hand corner, infectious diseases is very small. In fact, in the 2020 report, there's only 4 mentions of the word pandemic. This year's report, in the middle of a global pandemic, there were over 143 mentions of the word. But even so, it comes second to the biggest risk, which is still recognized as climate change, which is still top concerns. Now, we may think that space science and Earth observation is the domain of physicists and engineers to explore the universe, but actually the users of space data, especially Earth observation data, will find either from a smaller or larger extent that Earth observation has a part to play in every aspect of these risks here. But it's also, I think, useful to recognize that Earth observation, climate change, and looking at the Earth system actually has real world potential impacts. And because of this chart, I think it highlights and represents the real challenge in tackling climate change. And that's that climate change is highly complex, interdisciplinary, international, and interconnected. And this makes it very difficult to find simple solutions. And I think, as I mentioned, this is definitely the case for climate change, because the conceptual science behind global warming is relatively simple to grasp. Effectively, certain gases absorb radiation in the infrared and they re-emit this radiation. And this, in turn, can create a greenhouse-like effect. And in fact, it was so simple that actually it was the French physicist Joseph Fourier in 1824 that was the first recorded person to suggest that changes in the atmosphere could augment or change the temperature of the planet Earth. In 1861, way 150 years ago, Irish physicist John Tyndall showed that water vapor, as well as certain other gases, do actually create climate house-like effects. And in 1896, Swedish chemist Arrhenius was the first to suggest that coal burning would lead to significant impacts to the changing of the environment that we live in. In fact, he went on to calculate that doubling CO2 in the atmosphere would lead to a warming of the planet by a few degrees. Now, this was over 130 years ago, and this is exactly what we see. So why is it taking us so long to prove this? Well, in main, the difficulty has been in this, demonstrating what Fourier, Tyndall, and Arrhenius were trying to suggest. And it's because there's a lot of natural variability as well as complex feedbacks that we need to observe, model, and understand. And we also need to be able to do that on large enough scales of observation using standardized methods, using high enough accuracy of measurements that we can trust the data. And finally, we need to be able to do all of this over long enough time periods that enable us to see the warming trend on top of natural variability and feedbacks. The second huge challenge, and this is not to be underestimated, is in how we communicate this effectively. Because as I've mentioned, climate change affects and impacts everyone. And because it impacts and affects everyone, from politicians to business owners to your next door neighbor, everyone is a stakeholder and everyone has a role to play. So convincing everyone, even those who are not scientifically literate, those who are reluctant to make change, has to be done in an effective way. So these climate stripes at the bottom of the picture have been generated by researcher Ed Hawkins at the University of Reading and have really been a very simple, impactful way to communicate the science of climate change in a way that is intuitive to grasp. And so it's vital that Earth observation plays a role in both evidence gathering and communication. The ability to monitor and validate models with real-time observations on global scale to not only validate models, but allow environmental scientists to research the relationships between the different parts is in main what we do as space scientists, not just in the UK, but across the world. Now, this sequence of imagery taken from the European Space Agency shows something called the Climate Change Initiative. It's an area of science, climate change, that the UK really leads on, but it has to be done as an international community. Because as I've said, and I'll keep reiterating, climate change impacts every aspect of the planet that we live on. So being able to observe it using observational systems in space to be able to look at how the atmosphere, the biosphere, the cryosphere, the hydrosphere, and the lithosphere, the five spheres that I call, really interact with one another to promote in a feedback way, either constructively or destructively, to help improve or destructively look at climate change. Now, I want to just show one area of science that we are working on, that I've been working on for the last 10 years, which is in looking at the biosphere and how global forests are a massively important role in both mitigating and adapting to climate change. Forest degradation, along with forest deforestation, are placed second to the burning of fossil fuels. They account for about 15% of anthropogenic emissions of carbon dioxide. But there remains a lot of different questions. Are planting and reforesting schemes the right decision? And if so, which trees should we plant and where? So if we take these two scenarios, on the left, we've got the Amazon rainforest in Brazil, and on the right, we've got the highlands in Madagascar. These are two areas of research, places in the world that we are using Earth observation to explore and look at the differences in the landscapes. Now, these different landscapes have very different ecosystems. So the questions are, should either of these be reforested? Maybe it's better to leave them alone. Which is better at holding carbon, which is better for biodiversity, and which is better for the people to live within it? How can we make decisions in conjunction with the local communities that see this landscape as home, as well as a source for employment? So it's only really in the last few years that we're gaining a better understanding of Madagascar, the grasslands, how much more value they hold than we had originally thought. And it's through the work that we've been doing alongside partners in Brazil that we're performing in-field measurements, taking observations from space to help understand the changes in the environment. But we're taking this further to work to create fully interdisciplinary working groups, working with anthropologists and social scientists to understand the needs of the indigenous population, botanists and biologists to understand the biodiversity and the importance of the endemic species, and policymakers and economists to understand the impacts of these decisions that are being made. Now, one example of the complexity is that in 2001, I spent 3 months working in a scientifically unexplored part of Madagascar, just around here. And what we were doing is we're measuring and monitoring the different flora and fauna of the species in this area. It had nothing to do with monitoring or regulating how the communities worked in that region. That's not what we were there for. However, local communities base their livelihood on making charcoal, cutting down forests and burning the wood. However, in the short 3 months that we were there living in the forests, they accelerated the production as they thought we were there to stop them. These sequence of images are taken from Landsat from 1979 to 2019, showing not just the local deforestation that we experienced, but the wider geographic impacts of deforestation. And like every part of the planet system, it is just that. It's a system. A change in one component impacts another. The loss of trees destabilizes the soil. The soil is then lost through rain events, as you can see, as it leaches and bleeds the soil into the oceans. The loss of the soil isn't just associated with loss of carbon, which supports the growth of trees. The carbon in the soil acts as a natural reservoir for carbon storage. In fact, we're really only beginning to get accurate models to be able to monitor and understand the terrestrial carbon storage potential. And this is in main because we've only really focused on the biomass that we can readily see and measure, the stuff above the ground, the above ground biomass. However, when we talk about carbon in the ecosystem, carbon is not just found in trees. Biological diversity refers to all life forms, and that includes plants, animals, microorganisms that inhabit the natural landscape. There's clearly a very complex interactions that occur between all of these levels. And as you can see, between all of these different examples of different landscapes, it's very complex. The carbon stored is very variable, and what you'll notice how much is actually hidden in the soils. In fact, approximately 70% of all terrestrial carbon is found in soils, which is very difficult to monitor and measure. Through global observations from satellites, we're only able to observe the surface. And if the biomass above the soil obscures the view that we're looking at from satellites, then we can't even see this. So this missing 70% in the environment is, I think, the equivalent of the missing 70% mass of the universe. This is an environmental dark matter challenge. This dark carbon is one of the next biggest questions in climate science because it's such a big uncertainty and such a big unknown that it could really impact our future predictions for climate change. So where does this leave us? Well, through global observation systems, campaigns, both from space and on the ground, we've gathered scientific evidence for climate change. We've monitored impacts of the climate change, and we've provided data that drive climate models that help us understand the likely future given certain emission scenarios. And this was just the first part of the challenge, because in collaboration with all the Earth system scientists from every discipline, we've actually pooled our knowledge to create this vast IPC document, the Sixth Assessment Report. This provides the latest up-to-date scientific evidence behind climate change. And now the Earth observation is clearly not the solution, but is one important part that is needed to better understand the impacts of climate change, which help us to generate actionable evidence that underpins policy-based decisions. And that in itself helps us to understand how we can mitigate and adapt to climate change in the future. But effectively, evidence, especially from Earth observation, is nothing without action. And as Albert Einstein implied in this quote, but for very different reasons, evidence is very much nothing without action. Now, I didn't really want to leave you with this sinister and fairly downbeat message, so I thought I'd leave you with a message from Hemingway instead, that Earth is a fine place and definitely worth fighting for.
Thank you so much, Hugh, for this great presentation and for sharing with us all those amazing images from Earth.
You're welcome.
We had the first question in the chat from someone who want to learn more about Earth observation, and who was asking if you would recommend any textbook regarding technical understanding of the instrumentation used in Earth observation satellites.
There are some amazing texts. I'll pop some references into the chat in a second, but there are some amazing references, especially from the instrumentation side. So we as humans are very incredible in terms of our capability, being able to see in colors, being able to data process, and being able to do that like in 100 watts. And so all of our techniques that we're trying to recreate for space observation, for remote sensing, is really kind of a poor imitation of what we can do in humans. But actually, there's stuff that we can do in space that we can't do as humans. We can see in different wavelengths, and we can see, we can digitally capture it and store it for later processing, and we can't do that. And there are a few books that do an incredible job at actually describing the kind of those complexities and what we need to do to develop space instrumentation to observe not just the Earth, because actually the same techniques that we use to observe the Earth are used to observe deep space. Used to go to different planets. They're the same kind of techniques, same kind of instruments. But yeah, I'll put some of those links into the chat in a second.
Thank you so much. And you also mentioned the Clean Space Initiative. No, the Climate Change Initiative, sorry. I don't know if you would like to tell us a bit more about this.
Yeah, there's a lot of different work going on. The European Space Agency, the Climate Change Initiative, is just one global brand for actually UN activity linked with NASA, but it's kind of a global observation. And we use kind of UN mandated activities to try and bring together these data sets curated in a way that is that means that we can rely on that data. So we have things called essential climate variables, which are the biggest kind of uncertainties and the biggest variables that drive climate change that we need to monitor. These are things we can look up online. So again, there are great references online rather than me describing them all in detail. But these are the one thing to say is these are global activities that take place. And as our membership in the UK with the European Space Agency, we link very closely with those programs of work.
Okay, so thank you very much. And maybe can you tell us a bit more about your background and what brought you to now be working on Earth observation?
Yeah, no, it's really interesting question, especially from an early career perspective. I think I am definitely a planetary scientist, and I do count myself as a planetary scientist. Developing instrumentation. Oh, so my background is building instruments to look at water vapor on Mars, right? But as I said, Earth's a planet too, and water vapor is a climate gas, and we can use those same techniques to observe the Earth system. Now, serendipity goes a long way in scientific careers, and because it tends to be a bit of a random walk. If you have a passion, go for it. But I mean, the way that I think most scientists develop their scientific career is they see something that's interesting, and then they'll start to research it. And when we have that flexibility and privilege to apply for funding and get funding to enable us to explore things, develop new instrumentation, to take that instrument to different places. So I've been lucky enough to build instrumentation for space, but also to go to Brazil, China, Madagascar, to use Earth observation data, ground sampling for validating the data sets. It is incredible to think the random walk, the random journey that a scientific career can go on. But I think that's the same no matter who you are. I think serendipity goes a long way. Just follow your passion and just keep plugging at it.
Okay, maybe do you have any last advice you would give to an early career who thinks they are interested in working in Earth observation or something related to climate change, but do not exactly know where to start on which?
I think there's a couple of specific ones that actually have come out of me writing this presentation. Is that my thinking now is really much, previously back in the day when you're doing climate change, you're learning about a specific area of science. You're very narrow in your kind of field of work. But actually, I think climate scientists these days have to be prepared to communicate their research. Environmental scientists, not just climate scientists, environmental scientists have to be prepared to communicate the impacts of the work, because I think the impacts of climate change and environmental science are so dramatic that I think you can't keep that data to yourself. We can't just rely on publishing and moving on. I think we have to force ourselves to work in interdisciplinary ways with people who we're not familiar with, in areas and in research domains that we're not familiar with. And I think it's actually through that you can strengthen research ties and develop some really interesting new collaboration, because it's kind of at that interface between different disciplines that you can make some really remarkable discoveries. And the other thing I would kind of like to share is that there comes a point, and I'm now lucky enough to be able to say that I can do this, that I can now choose projects where I work on research projects that I want to work on with people I want to work with. And I think once you've got that, once you're at that position, once you have that privilege, it becomes a completely different different thing for research. Because I have been stuck on projects where, I'm not ashamed to admit this, where the team has been incorrect, or it's not something I've been passionate about. So for those reasons, it makes that scientific kind of journey of discovery quite difficult. And when you have the ability to choose projects to work with people you want to work on with, it makes such a difference.